Hello everyone. Uh, this is a mini lecture series on tensors and tensor calculus. The reason I'm making these lectures is because there are certain things that cannot be explained by just writing. Uh, so uh, someone explaining it to you make it very easy to understand. And I wish there is someone who would do this while I was learning the topic. Mm, So and now so I wanted to include many details but couldn't for some reason. So uh, I hope this mini lecture serves as a closure to the entire project. So now, uh, before embarking on the actual topic of tensor calculus, I would like to um, uh, discuss about some preliminaries, that is linear algebra, not entire, not extensively, just some definitions of vectors, covectors, basis, and yeah, that's all. So, uh, so until I want to talk about vector spaces first. So, so what is a vector space? So, a vector space. Sorry about my writings. Uh, a vector space V is a set of elements that uh, follows uh, some properties. So vector space is a set of elements with two operations. So with two operations. So the operations are plus operation and uh, dot operation. So a plus is defined as if we uh, if we have the real number, if the field of real numbers are, and if our vector space is V, then plus is defined as a pair with one element from R and another element from the vector space itself, and it maps to so- uh, sorry the plus map is defined as a pairing of two elements from the vector space, and which map it takes a pair xy which belongs to the and xy belongs to the vector space, and it maps it to an element of that vector space. So, for example, if we have A which is in B and B which is in B, then the plus element takes A comma B and maps to another element. It maps to an element A plus B which belong to the vector space. So the dot or the times what it does is takes two elements, one from the real vector field and another from the vector space, and maps it to the vector space. For example, uh, so the real vectors field they two constitute a vector space. with scalars with the same operations. So if we take an element from our cell lambda and an element from v say a, the dot takes it to lambda dot a, which is the simple scalar multiplications we do in real numbers. And the properties of the elements that the properties that make sure the set is a vector space are the followings. So the commutative law, commutative law for the plus, and it is so just so if I have uh, two elements v and w from our vector space v, so then the commutative law says v plus w is the same as w plus v. Uh, then we have the associative law. Or plus. So if we have three elements from our vector space, VW and let's say X, since in V, then V plus W plus X is the same as V plus W plus X. Then we have the existence of identity. So the identity is 0. So basically the identity, it's the additive identity, if I'm not wrong. That which means if you take an element and its inverse and add them, it gives you the identity 0. But if we haven't defined the inverse yet, so but we'll do in a little bit. So the existence of identity. So v plus 0 gives you v. Since any operation with the identity left the things just as it is, just as it is. So that's the additive identity. And then we have the inverse, additive inverse. So the additive inverse, which is we have already said. So there is an element which if we add it with the element, we get our identity. So in that case, it is minus a, gives 0. So the additive inverse of a is minus a. Then the distributive law. Here a is a scalar or maybe C. Uh, uh, sorry. So this is the same. In is scalar. Sorry. We have another element. Mm, then we have our multiplicative identity, which is 1, because if it acts, if we dot it with an element with of v, let's say v, then it gives the same thing. Yeah. So that's so these are the properties of a vector spaces. So any set that follows these properties are called vector spaces. And you, yeah, yeah. And the elements of that space is called vectors. Now, this is not. It doesn't have to be. It doesn't necessarily have to be the same as the vectors we already know as the direction vectors. Uh, yeah, even though they too made a vector space, but it is not necessarily a direction vector or something uh, that we have seen uh, in our physics uh, uh, so far in our physics study. Uh, so maybe I should give some example of vector spaces. Mm. A, a polynomial of degree n. Let's see, 1 plus x plus, that's x cube. This every polynomial of a degree 3 polynomial of degree 3. I mean, in general it's n, but for uh, I'm giving an example for just n is equal to 3. Constitute a vector space. And the basis of that vector space are, oh sorry, I haven't talked about basis, sorry. So let me define what a basis are. Basis is. So a vector space has a set of elements. Say our vector space is V with uh, dimension, and a dimension is just if an element of V can be written as, let's say, x1, x2, x1 comma x2 comma dot. And so if this list has n elements, then our vector space will be called a vector space with dimension n. And now uh, there are many elements with in the vector space, and and of and there are some specific list. So this is called a list. So there are some list uh, which can be used to produce all other elements of the vector space just by uh, just by some multiplying every element of that list with some scalars and combining them in different way. Basically a linear basically a linear combination of them will produce all other elements of the vector space. So such a list is called a basis. So for example, if we uh, let's take our usual R3. We know it looks like this in vector notation. So ijk. This ijk is basically the unit vectors. And that which means that you already know what that means. So if we want to write an element, let's say 6i plus 4j plus 3k. Look how we write them. We write them as 6i. So in the I direction, it's 6 times I, 4 times j, and 3 times k. And you know that all the elements in R3 can be written as ij in some linear combination of ijk. That's why we call ijk as our basis. But these ijk's are basically 1, 1, and 1 because uh, because you already know what. So this in list from these things, this it can be written as 6, 4, 3. So in R3, one such list is 1, 1, 1, and there are many other lists which can form a basis, which can act as a basis on R3. But we usually deal with this. So what I was saying before, a polynomial of a set of all the polynomials of degree 3 constitute a vector space, and 1 x squared x cubed. This list act as an basis of that vector space. Let's take an arbitrary polynomial, say 1 plus 5x plus 3x squared. And now you'll see that this can be written as it then in terms of some linear combination of this list. That is 1 plus 5 times x plus 3 times x squared plus 0 times x cubed. You see this 1x x squared x cubed. I think it's clear why this is the basis of this act as a basis of the polynomial in the set of polynomial of degree 3. So, so the point is, if we take an element, let's say if our vector space is V, if we take an element of V, say W, we can write it as a sum of linear combination of the basis of that vector space. If we choose our basis to be epsilon 1, epsilon 2, dot 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 epsilon n, and our dimension is n, then we can write W as some linear combination of, let's say, W1, epsilon 1, uh, W2, epsilon 2, dot dot dot. And the reason I'm using the upper index is there is a reason why I'm using this. I'll come to that later. So I can write it as summation of, yeah, higher, sorry, n goes from goes from 1 to n. What? Sorry, I would be more. So I goes from 1 to n. So there is a convention called instance summation convention, where we do not write this summation if we do not write this summation whenever we see there is a repeated indices, as the repeated indices is I. So it's clear, it should be clear from this that there is a sum hidden. There is a sum, but we don't write it. So we write it as this. And in vector space, the coefficient, the scalar coefficients are written as upper indices, and the bases are written in lower indices. So it's upper indices of coefficients, and lower indices for bases. So this is our vector space. And now let's talk about covector, or a dual vector space. So a dual vector space. So to define a dual vector space, we need a vector space. Let's say our vector space is V. Now its dual is defined as V star. It's a map. So V star is a map that takes an element from V and maps it to R. I think it looks familiar. It's like a function. Sorry, it's not. It's a function. So let's say V is our vector space, and there is a function that takes an element of V and maps it to R. R is in the real field. So all such functions may constitute a vector space. All such functions. And this vector space is known as the dual vector space, which is written as V star. So we have a vector space, and there are many functions which there all the functions which takes an element of from our vector space and maps it to a real number constitute a vector space themselves, which is known as the dual vector space. But there is yeah, now this dual vector space also has a basis, of course, and we want this basis to be uh, to follow a specific rule, that is, let's say the basis of the dual space is fi, sorry, f1, f2, fn, and the basis is the basis of v star, and the basis of our vector space V is epsilon1, epsilon2, epsilon n. and we want this, and we want that when we want f1, when f1 acts on e epsilon 1, it gives us 1, and when f1 every other time it gives 0, such as it will be. So in general, we want fn epsilon n to be 1. So let me write it like the Kronecker delta notation. We want this n m. So the definition of this Kronecker delta is it is 1 when n is equals to m, and 0 when n is not equals to m. So this is, so yeah, this is how you want our basis of the dual space to be. Now you might have noticed write how I wrote the basis of the dual space. I use the upper indices for the basis. So let's say we have let's take an arbitrary element from our dual space V star, let's say f, and we write it as the summation of linear combination of the bases. Let's say 1 a1 f1 plus dot 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 af an fn, and use this Einstein summation or convention, we can write it as an fn, and here an, the coefficients of are written in lower indices, and the bases are written in upper indices. So it's the opposite of the vector space notation. An element of a vector space is called a vector, and an element of a dual vector space is known as a covector. So yeah, so this is all we have to know for now from linear algebra. Now we can move on to so let me make another note. Maybe I should do it now. So we know a vector is from a vector space, and a covector is from a dual vector space. Now there is a convention. Uh, hmm, so we know vectors can be written as the coefficients, the components. So I'll use the word component from now. Uh, uh, v nu, epsilon nu, and the covector can be written as f nu. Sorry, should I write it? So omega. Let's see, omega no, eta nu f nu. So this component with upper indices is known as the contravariant index. Basically, we call a raised index a contravariant index, and the lower index a covariant index. So this and this are contravariant index, and this is have a uh, covariant index. So basically, vector components of vectors have contravariant index, and components of covectors have covariant index. So this is so most of the books on mathematical physics use this convention, and so we will use it. Uh, so we will also use this convention from now on throughout the whole series. Thank you. In the next lecture, we'll talk briefly about differentiable manifolds.